Some of the questions you really need to do some good work to solve them. Yeah. And quite challenging. Yeah. So I hope you spend a lot of time, study the materials and solve them. Yeah. Here, I may like to give you hints for some of the questions. Yeah. There is one I feel very challenging is this. All right. Look at this question. All right. Question number 23. Given a 114 element array, what is the minimum number of comparisons that you need to find an element that is among the top 5 in the sense of values? Yeah. Think about if we sort this array, all right, sort this array. Top, yeah, so top means highest value. Okay, and the bottom, lowest. All right. Then we want to get top 5. One of the elements in top 5. Yeah, it could be 5. Now the question. So the hard part is, if you do not find the right way, you may end up with a large number of comparisons. Yeah. So you just find one that is among the top 5. You may use too many comparisons. Yeah. Our goal, we want to find the minimum number of comparisons. Here, minimum number of comparisons to find this answer. Okay. Yeah. But you may not have a good idea. So when you look at this question, most likely you do not have any idea how to solve it. All right. So here, let me give you some hint to help you find the right way to solve this question. Yeah. All right. The best way to find a solution here, you need to connect this question to some existing solution we have learned. All right, yeah. So which one is closest to this one? Yeah. So let me point that out. We have learned one problem that I refer to it many times in this class. So what is that problem? This one. Finding the minimum of an array. Right? This question. Yeah. This question, although very simple, but we have used this one many times in this class. Here, for this question, can you see the connection with our current question, question number 23? Yeah. Let me point it out, the connection. All right. let us consider a general question. Okay. Given an array with n elements. Okay. We want to find a solution using minimum number of comparisons for an element. That is among the top K. How about that? Top K. Okay, yeah. Now, for this general question, when K equals 1, that's top 1, right? When K equals 1, that's top 1. Top 1, that is the maximum. Or, you know, if you arrange top for minimum or top, you know, yeah, we can change maximum, you know, similar, you know, the same solution. Yeah, maximum. Yeah, then it's top 1, right? Yeah, maximum, top 1. And our current question number 23, K equals top 5. How about that? So that means these two questions are closely related. Okay, all right, so that's first thing. That means your understanding of our finding the minimum question can be used to help you solve this question. All right, yeah. And the way we used to find the minimum, we use the elimination method. Elimination method. Okay, yeah, that's the basic method we use to solve that finding the minimum. All right, yeah. So look at how do we find the top 1, the maximum, the largest one? If we can eliminate n minus 1 elements. Then what? We find the top one, right? Yeah. Now can you use the similar? If we can find a way to eliminate certain number of elements in this question with 114 elements, find a way to eliminate certain number of elements. All right, yeah, try to get that similarity analogy here. Then the remaining among the top 5. How about that? Okay, think about that. All right, yeah, but still you need to do some important work. Yeah, here I give you the connection. Yeah, point to the right direction you can go, but you need to make that critical step. The critical step still there. I didn't tell you here. Yeah, but you need to find it. All right. Yeah, the direction is, what I give you the hint here. Yeah. All right. Any question? Let me know. Any question? Yeah. And also, if you have question on some other homework questions, you can also ask me. Yeah. But here, I cannot spend too much time in today's class on our homework assignment. Yeah. I just, give you 2 more minutes and see if you have any question here. All right, midterm exam. Yeah, all right, good. Yeah, let me tell you the midterm exam. First, you need to submit your homework assignment 1. Yeah, because the main reason I give you homework assignment, let you have practice, plenty of practice before you can do the midterm exam, right? So the due date 20th. All right, so after you turn it in, I grade it and I return your grading results, and I may do some review after that. All right. Then we submit answer, just type in the Word doc. Yeah, okay, Word doc. Yeah, another thing. Yeah, that's one way. But another way people submit, you print out, yeah, print out on paper. So, use your pen, so write answer on it, then you send me images. That's another. Oh, did not receive. Oh yeah, I'm start grading. Yeah, it takes some time. Project 1, at this point, I did 3 students, first 3 students. Then, I have a grader. So I need to, create a guideline for my grader. Then my grader will do the remaining grading for the project 1. Yeah. Yeah. Usually it takes some time. Yeah. All right. Yeah. So the image scanning, image, yeah. I mean, just anyway, right. Anyway, so you send me, submit the bottom line, just let me know your answers. Yeah. Let me know your answers. In sometimes PDF file, image files, Word files, all okay. For the Word case, yeah, the thing is, make sure your formulas can be displayed in the right way. All right. Yeah. Sometimes I notice some distortion in formula display. Yeah. For other ways, PDF scanning pictures, other ways, usually the formula display is fine. Yeah. All right. Any other questions? Yeah. Then I will start explanation of homework assignment here. Yeah. Yeah. Still, there are many other challenging questions. So you really need to do some hard work to do well in this assignment. All right, let me get back to the midterm. So after that, yeah, because I will say the midterm will be approximately around the end of this month, approximately the end of this month. Yeah. Yeah. around, could be minus plus 1 or 2 days. Yeah. The end of this month plus or minus 2 days, approximate that. Okay. Yeah. The main thing is I try to make sure you get it ready, pretty much get it ready for the midterm. All right. Yeah. All right. So I want to stop this topic right here. Yeah. And we move to our next topic. Binary search and selection problem. Binary search first, B.1, and we use the elimination idea to understand this problem. I think you are familiar with binary search. Everyone here is familiar with binary search. Yeah, but here we like to study it using the divide and conquer approach. Okay, yeah, it is a basic fundamental search algorithm, very important. So let us study it another time, and this time we try to get very good understanding. All right. Problem description. Our problem number 11. Yeah. Given an ordered array. So this time, ordered array. Okay. Yeah. Very important. Yeah. Expression in this way, and a search key V. How to find an index I such that V equals A of I. Yeah, so that's the question description, and the reference on our textbook, yeah, section 4.4, page 150. Yeah. Let us do analysis. Yeah. All right. Idea, the strategy idea, all right? Reduce the problem size by the ordered data property. Yeah. Our data has a special property. Yeah. All right. Yeah. The data is sorted in ascending order. That information is important. Okay. So we should take advantage of that useful information. Yeah. Yeah. Remember, when we solve another problem, yeah, that's that problem called what's that? Unique element problem. All right. In that question, we use two methods, right? The second method, in order to improve the efficiency, we sort our data. We sort our data first. Okay. Yeah, we spend quite some time. So there is a, pretty high cost for this sorting step. But here, the good thing is we do not need to spend any time. We have a sorted array. All right. So that means this requirement is very useful. We really need to take advantage of it. Yeah, because it's like something valuable you get free. Okay. This sorted data is very valuable, and we are given without any cost. It's free. So we really need to take advantage to use this condition well. All right. How to use this condition? All right. We want to use the elimination method. Yeah. So you can see in this class, the most frequently used method is this elimination method. Okay, all right. Question: how can we take advantage of the ordered data property? Right? We need to have some implementation idea here. Yeah. All right. Let us explore the order property by drawing some diagram, and we want to get some visual understanding. Yeah. All right. So let me draw this array in this way. Yeah. In ascending order, A0, A1 through AN minus 1, and also the given key V, we want to use it to do comparisons with the given elements. All right. When we do comparisons, there are many different ways we can do comparison, right? V is compared with the last element, or with some element in the middle, or with the first element, right? Yeah. For all these cases, we want to see which one is the best. Okay? Yeah. Which one can give us the best result? So that's something we like to have. So what do you mean best result, right? Yeah. Because that description is still quite vague. We want to have some more accurate description as the best result. Yeah. If we use this elimination idea, the best result means we can eliminate the maximum number of elements that we treat as the best. The more elements you can eliminate, the better the result you get, right? Yeah. That understanding looks right. Yeah. Yeah. Because if in every step we can eliminate the maximum number of elements, then we will get our final result in the fastest way. Yeah. So that's our basic understanding. Yeah. All right. Now the question, another question. After one comparison, how many elements can be eliminated? Here, we just look at one comparison. That's enough. Yeah, because we just use one typical comparison as the representative. And we want to see what is the best way to eliminate the maximum number of elements. In one comparison, we can see that. Okay, in one step. All right. Let us get into the details in the comparison. Yeah. If we look at the last element, V is compared with the last element. There are two possible cases. All right. The first case, the best case. Now, the first case, that is V greater or equal to A sub n minus 1. If this happens, think about how many elements can we eliminate? How many elements can be eliminated, right? Because V greater than, basically, we can eliminate all these elements before the last element, right? Yeah, last element, because still there is a possibility V equals the last element. So we cannot say we eliminate the last element. Yeah, but we can say eliminate all the elements except the last element. All right. So that's why we say the best case, because that's the maximum number of elements we can eliminate. All right. But you may not be able to always get the best case, right? Yeah. Sometimes you do not get the best case. So there is another case you need to consider. Right? So other cases, when V less than A sub n minus 1, when this happens, think about how many elements you can eliminate. Only the last one, right? Think about in this other cases, you can only eliminate the last element. Yeah. And the remaining n-1 elements cannot be eliminated, and you need to consider them, right? So in this case, only one element eliminated. In that case, n-1 element eliminated, right? Yeah, huge difference. Yeah, all right, think about it. But this possibility, we need to seriously consider it, right? You cannot ignore this case, right? Yes. So here, there is something like Murphy's Law, yeah? Because this situation is pretty much like, the famous Murphy's Law tells us, so that is, anything that can go wrong will go wrong, right? That's the, Murphy's Law, yeah? But here, this other cases, this part, we don't like this case happen, right? Yeah, because we like the best case happen. We don't like the, worst case happen, all right? But this could happen, right? Yeah, and the probability that this worst case happen is very big, much bigger than the best case, right? So that means in this situation, the way we choose the last element for our first comparison is not good. Is not good because there is a huge worst case you need to consider. All right, yeah. So in order to avoid this kind of situation, we want to find a better way to do our first comparison. Now, the better way should be, even for the worst case, we can eliminate the maximum possible number of elements. That's what we need. Now, you have to consider the worst case, right? You cannot always consider the best case. So here the question is, even if we consider the worst case, still we get a pretty good result. That's what we need. All right, so think about that understanding. All right. Then, now we modify our first comparison way. We like to compare the one right in the middle. Yes, this time we choose the first element to be compared is the element right in the middle. So that element has a name called a median. We compare V with the median of the array. What is the definition of the median? Okay, the definition of the median, it depends on you have odd number of elements or even number of elements. Okay, if you have odd number of elements, yeah, that is the one right in the middle. So no question about it. But think about when you have even number of elements, how do we define a median? Because there are two elements in the middle, yeah, in the center locations, two. Yeah. And these two people call left median and the right median. Okay, two medians, all right? But the left median is the default median, okay? Default median, yeah. So if people do not say left median or right median, we mean left median, okay? Yeah, because we want to avoid ambiguity. We like to have certainty, right? Yeah, the certainty is we use the left median as our default median for even number of elements in the array. Okay, all right. So now we use this median concept. Yeah. So we feel if we do comparison V with the median element, then you have two cases. Okay? Left case and a right case. Yeah. Let's say in this way, left case and a right case. But these two cases, they have almost the same number of elements when you talk about elimination, right? Either left case, right case, you can eliminate the same number of elements. May not be exactly the same, but difference is only one, right? That one difference is not significant. So we don't worry about that one difference. Or we can say up to one difference. Yeah, 1 or 0. Yeah, sometimes 0, sometimes 1. So that's very little. So we can comfortably ignore it. Yeah. All right. So here you can see choosing the median as the first element to be compared with, that is the best way to do the elimination. Because even for the worst case, even for, we have two cases, okay? Yeah, one slightly better, the other slightly worse. Even for that slightly worse case, it's not too bad, right? Yeah, even for that slightly worse case, we can still eliminate approximately 1/2 of the elements in the given array. How about that? That observation, that property. Every time you can eliminate approximately 1/2 of the elements. Okay, yeah. But if, whenever you have a chance to do comparison, always compare with the median element. All right, that's the essence of this binary search. Yeah. All right, so here we like to, make our logical reasoning, thus thinking in some formal way of thinking. That is, we call it balancing principle. Because our first try, this try, the reason it is very bad is for these two cases, the data is distributed not in a balanced way, right? Extremely unbalanced. Yeah. Data distribution for different cases is extremely unbalanced. That's the reason we have poor efficiency. All right. Then for the median case, the data distribution for those two cases extremely balanced, right? Yes. Closest to the most balanced way. We can call it the most balanced way. Yeah. Okay. So if we can, so here, if we follow this balancing principle, that is, whenever we have a chance to distribute our data, we will choose the most balanced way to distribute our data. If you follow that principle, most likely you will get the best solution. Most likely. So here I do not say 100%. Probably 90-something% you will get the best solution. But still, you have some very small percentage chance you may not get the best solution. That's possible. Yeah. All right. Yes. So with that, then our conclusion, yeah. Every time you can throw away 1/2 of the elements. Yeah, that's the elimination. Yeah. So this is the result of our elimination. Okay. All right. So with this understanding, let us do the remaining work of our binary search, and at the same time, we'll look at the efficiency analysis. All right. Okay. Now, let us understand binary search. When we go through the whole binary search at the same time, we do efficiency analysis. Okay, yeah. We want to count the number of comparisons for the worst case. Here. Worst case, not the best case, because best case is trivial. Your best case is V equals the median. That's your best case, right? So V equals the median. Then one comparison, you get a solution. That's trivial. So we don't consider this case. All right. The worst case, then we need to spend a lot of time to consider the worst case. Yeah. All right. Let's draw this diagram. We assume this line segment represents an ordered array, ascending order, right? The first time this is our V, our key, compare it with the median element. All right. After the first comparison, we eliminate one of the two subarrays, right? Yeah. Either the first subarray or second subarray. We can drop it from our consideration. Okay. All right. After we drop the first subarray, we have data that is approximately 1/2 of the original data size. Yeah. Half of the line segment. Yeah. The second time, we do another comparison with the median of the current subarray. Yeah. The result, still, we drop 1/2 of it. Okay. And we do this again and again until we get to the last step. We have to stop somewhere, right? But where to stop? At this point, we do not have a good idea. Yeah. After how many number of comparisons we have to stop? At this point, we couldn't figure out. Yeah. But later, we need to figure this number out. Okay, yeah, because that is important. This number is important. Yeah. Let us draw this chart to understand the data reduction procedure. Yeah, all right. Number of ops, number of comparisons. The first comparison that cut the data size 1/2 of the original. Okay, second comparison, then the remaining data size 1/4 of the original, and so on. After case comparisons, then the data size to be considered, it becomes m over 2 to the kth power expression. Yeah. So you can see the data size is reduced quickly. Right? Every time divided by 2, cut it in 1/2. Yeah. So this reduction is pretty fast. Okay. All right. Then now we like to figure out this K and see for what K we reach the end point, the last comparison. The end. Yeah, that number is important. We need to figure out. Okay. So the question, at what time should we stop splitting? Okay. Can you find condition? You know, we can call it stopping criteria. Stopping criteria. Okay. Yeah. You have to stop. It does not make sense for further splitting. We need to find that condition. All right. So let's look at this. After the last comparison, let's look at the data size we have. Yeah. Based on our, the chart here, we have some suitable data size we can use for our analysis here. Think about if the data size less than 1, should we do further splitting? Yeah, because look at this fraction. It is a number, right? There is a possibility this expression less than 1, right? When k is sufficiently large. If it is less than 1, that means it can only cover, yeah, so you have an interval. The size is this length. This length, yeah, that's the size. Length of this small line segment, that's the size. If the size, the length less than 1, it can only cover one integer, right? Can cover one data item, not two. If you have two data items, the difference between two data items, that's 1. All right. But your interval is less than 1, so you can only cover one element. If you have only one element, there is no reason you want to do further splitting. So you have to stop. So here, this condition gives us the stopping criterion. You have to stop if you detect the data size is strictly less than 1. Yeah, strictly less than, not equal to. If equal to 1, you have a chance to here. This is equal to 1. You have chance to cover two elements, right? Two elements. So you need to do one more splitting. Yeah, but here strictly less than 1. No reason to do another splitting. So that is the stopping criterion. All right. So with that, because this is our size expression, the size, the current size, this is current size. The current size is strictly less than 1. The second one is the previous size. Previous size is greater or equal to 1. Okay. If you find this kind of k satisfying these two inequalities, that k corresponds to your last round comparison. That's the accurate analysis we need here. All right, yep. Since we have this inequality here, we can write an equivalent. Yeah, this one we just remove the common denominator, so we get a more friendly expression. Same equivalent condition, but this version more friendly. Right? Yeah. So then after that, we solve this inequality, or these two inequalities, we can get new expression. This time we try to get our k out, because k is our our goal. K expression is our goal. All right. So yeah, in that way we have to use log base 2 expression for m. Yeah. All right. So then next, yeah, here for the worst case k, it is satisfy this inequality. Okay. Yeah. But inequality, when we use inequality, that means still there is some room for k, right? The k could be in a range. So that expression still we feel not quite accurate or precise. So we want to make that inequality to equality.
If we use equality expression for k, then that is very precise, right? Yeah. So that is not a range expression. We know inequality, that is a range expression, right? In that range, you have some freedom to move around, right? But now, if we have an equality, then that is accurate, okay? All right, let us derive the worst case formula. All right, we start with the equivalent expression. Yeah, here, another way to write, the previous inequality, we can write in this way, okay? Yeah. Now, because this time we put k in the center, and the k has a lower bound and upper bound. Yeah, lower bound and upper bound. Okay, the difference between the lower bound and upper bound, look at the difference, is 1. Okay, the difference is 1. That means we can find an interval with length 1 to cover this k integer. All right. Yeah. Can we find integer expression for k? Yeah, because that interval can only cover 1 integer. Yeah. Because this is an inequality. Okay. Yeah. The left side inequality is strictly less, not equal. So that means this interval can only cover 1 integer. Okay, yeah. All right. So now we can write in this way. Yeah, yeah. Because look, why we switch back to the exponential expression, the reason is log base 2 of n, it's a non-integer, right? Non-integer. All right. And look at the expression here, we have integer expression. Yeah. Everywhere we have integer expressions. Integer expressions, we can do better, right? Yeah. When we consider the errors, we can do better for integer expressions. For non-integer expressions, the fractional part, it is not easy to control that fractional part. So that's the reason we switch back to the, exponential representation. Yeah. All right. Then look at that. All right. So here. All right. And yeah, look at the right-hand side inequality. N strictly less than 2 to the k. Can we write n plus 1 less than or equal to 2 to the k? Yeah. N is an integer. 2 to the k also an integer. One integer is strictly than another integer. Then we increase the smaller one by 1. Can we say this n plus 1 is less than or equal to 2 to the k? Look at that logic. Look at this logic. Okay. We know n is strictly less than 2 to the k. Then we can say n plus 1 is less than or equal to 2 to the k. Yeah. There is a possibility they are equal, but there is some bigger chance n plus 1 could be less than, strictly less than 2 to the k. All right? Yeah. That's the right-hand side. How about the left-hand side? Yeah. All right. So the right-hand side, with this new expression, we take natural log, we can get this. Look at that. Okay. Natural log on, we can get that. Okay. K greater or equal to log base 2 of n plus 1. All right. Then this side, look at that. Okay. Yeah. Because look at this inequality. Okay. Yeah. We take natural log, not natural log, log base 2, k minus 1 less than or equal to log base 2 of n. At 1 both sides, k less than or equal to log 1 plus, okay? Yeah, 1 plus log base 2 of n. That is this one, okay? Yeah. So we have a new inequality expression. K is between these two log base 2 expressions. All right. Now, the last step. How do we get integer expression? Our goal, we want to find the integer expression. How to get that? Okay. Conclusion, two formulas. Two formulas we have for the integer expression. The first one, yeah, K max, yeah, the maximum number of comparisons we need for binary search. K max is the ceiling function of the lower bound. Yeah, this is the lower bound. But we know k greater or equal to that log base 2 parenthesis n plus 1. So we should take ceiling function. That is the first formula. Okay, yeah. All right. Can we use the upper bound function? Upper bound function greater or equal to k. So we should use the floor function here. All right. So our second formula, k max, there is another representation. K max equals 1 plus the floor function of log base 2 of n. Yeah. These two formulas looks different, but they have the same value. Same value. Okay? Yeah. Because we know the integer between upper bound, lower bound, there is only one integer between, only one integer, k max, between upper bound, lower bound. Now we have two different expressions for this unique integer covered by that interval, right? So they should be the same. All right. Based on our analysis, these two expressions should be the same, although it may not be obvious, right? When you look at these two expressions, it's not that obvious. They must be the same. Yeah. And we can use mathematical induction to show they are the same. Mathematical. So we have this formula. Yeah. These two expressions are the same. Yeah. And this equality can be proved by mathematical induction. Okay. Yeah. Yeah. All right. Yeah. We have less than 10 minutes. Yeah. Yeah. Actually, in my notes, I have the mathematical induction part. Yeah. Let me see, because still we need to do a lot of work. Yeah. 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 The best case, we know one comparison. The worst case, we have this expression, 1 plus, yeah. Yeah, you can use second expression, the first expression equivalent, okay? Yeah, but after this class, you need to be able to identify that these two expressions are the same, okay? You need to know this, okay? All right, I may skip the mathematical induction part, yeah, because it takes too much time, yeah, at least half an hour. Yeah, yeah. At least I need to spend half an hour to, go through the details of that mathematical induction. Yeah. But here I like to talk about the average case. For binary search, how to calculate the average case. Can we say the best case plus worst case divided by 2? The answer is no. The answer is no for binary search. All right. The answer is no. We can, if we do this way, conceptually, it's not correct. Yeah. You may argue this expression is very close to average case. Even you make that argument, it is wrong. Okay. Yeah. Actually, the average case is slightly smaller. slightly smaller than the worst case. The difference is less than 1. The difference is less than 1. Slightly smaller than the worst case. All right? Yeah. All right. All right. But the question, how to calculate the average case? Yeah. Yeah. Let me see how much time I have. Yeah. A few minutes. Let me see if I can explain that average case. Here, let us do n equals 7. Just a simple example. N equals 7. Let us calculate the average case. Okay? Yeah. To calculate that, we assume we have a 7-element sorted array. Okay? In order to calculate the average case, let us draw a diagram to represent number of comparisons for each element in the array. Okay? Yeah. Here we assume V is in the array. All right. Yeah, V is in the array. So, yeah. And because for the general case, V is not necessary in the array, there is a probability that V not in the array. Okay. Yeah. In the array P, not in the array 1 minus P. Okay. Yeah. In general, we should consider this situation. Yeah. But here, let us consider a simple case. Yeah. We assume V is in the array. All right. So then let me draw the diagram. Okay. All right. If V equals element number 4, then we just need 1 comparison, right? Yeah. So this 1 tells us if V equals 4, 1 comparison. All right. Next level, if V equals 2 or 6, based on binary search, we need 2 comparisons. All right. Then the lower level, lowest level, bottom level, V equals 1 of 3, element 1 or element 3 or element 5 or element 7, then we need 3 comparisons. Yeah. So you can see all 7 cases are here. When we do average, we should do the average on all 7 cases. Yeah. Now let us write average formula. All right. Because 1 comparison, so here, so here, the first number represents number of comparisons. 1 comparison appears only once. So here, occurrence. Okay. The second number means occurrence. Occurrence is 1. 2 comparison, its occurrence also 2. Yeah, 2 cases. All right. 3 comparison, its occurrence is 4. Okay, occurrence is 4. Number of comparison number is 3. Comparison number is 2. Occurrence number. Yeah. So we do, the numerator, we accumulate all total number of comparisons. 1 times 1 plus 2 times 2 plus 3 times 4, then divided by 7. So the average case efficiency 17/7. 17/7. Look at this number, right? Yeah, this is just a special example. Yeah. For other more general example, we can use the same way to calculate the average case efficiency. Yeah. All right. Yeah. So try to understand this calculation method. Yeah. Because later in future sometime, I will give you this kind of questions. Okay. All right, so let's stop here today. And we have one topic left. I will quickly complete that part next time. Okay. All right, so that's it.